Okay, hello everyone, and welcome back to Programming Languages, Semantics and Verification. Uh, I have a couple of things that I should clarify before going on. So the first point that I should tell you is that there was a problem with the homework, basically. Uh, the due date of the homework is 25th of February, and I had mistakenly written 9th of February. So the second homework is due on the 25th. And the second thing is that today we were going to cover two-player games on graphs, but I decided to change this a little bit, and instead today I'm going to show you something very practical. And this is because I got several emails, to be more specific, 4 emails from people in this class who asked how these formal semantics can actually be used in the real world and how we can actually apply the tools that we learned, especially horse logic. So the plan for today is that I'm going to introduce you to a tool called Boogie, which is mostly developed by Microsoft Research and is actually based in Microsoft Research right now. And then I'm going to show you how we can actually do real world verification using Boogie. And another point that I should clarify is that for those of you who have already read Hoare's paper, you know that it claims that whenever a property or Hoare triple holds, there is a proof for it. And this had caused a lot of confusion because it seems to be contradicting Rice's theorem, which says that any semantic property of programs is undecidable, but this is actually not a contradiction. So basically what Hoare is saying in his paper is that if a triple holds, you can find a proof for it in his proof system using his rules. But this doesn't mean that there is an algorithm that can compute it. It just means that such a proof exists. So they're talking about two completely different things. So Hoare says that such a proof exists, and Rice says that finding these proofs is hard. Or actually, it's not just hard, but impossible. So these two things are not really contradictory. And the main difficulty when using Hoare's logic is coming up with the invariants. And today we will also see some examples of that as well. So with that being said, let me share my screen and okay. What's in his chat? So today I'm going to talk about Boogie, and this is the web page where you can download Boogie and install it. The installation is actually quite easy. You can easily install it on Ubuntu, for example, using apt-get. And now what Boogie is, let me first start by that. So Boogie is basically an intermediate language. So it's a specific language that is made in a way that makes verification a bit easier. And the idea is that instead of writing verification frameworks for every language, oh, is it better now? Okay, so yeah, the idea behind Boogie is that instead of writing a verification framework for every language, you can just use Boogie as an intermediate language and write your verification on top of Boogie. And then when you want to use another language, you just write a compiler or a translator that translates your programs from your source language to Boogie and then does the verification. And this has actually been done for a lot of different things. So there is, for example, C, C Sharp, Spec Sharp, and so on. And there are a lot of projects that use Boogie for proving all sorts of things. There is even an operating system which is completely verified in terms of type safety. And now what Boogie does is that it basically tries to apply Hoare logic, but it can't always do it straightforwardly because it needs to find the invariants. It also needs to uh, prove the implications and so on. So we had, for example, strengthening the precondition and weakening the post condition and so on. So these things are not really automated in Hoare's logic. And what Boogie does is that it uses an SMT solver. It uses Z3 for that. And an SMT solver is basically, you can think of it as a theorem prover, something that helps us prove logical implications. So that's what an SMT solver is. And I don't really want to get into how SMT solvers work. I just want to show you how Boogie works. Okay. So there is actually an online version of Boogie, which you can access at this address, riseforfun.com/Boogie. But it's usually non-responsive, and it's actually non-responsive right now. So I would suggest that you just install Boogie on your machine. Okay. Now okay. So let me show you how Boogie works. Well, what do we want to specify for Boogie? What we want to give it is basically a program which should be written in a language that it understands. And quite confusingly, the framework is called Boogie and the language is also called Boogie. So we have to write a Boogie program. And we have to also specify what it is that we want to prove about this program. So let's start by a very simple program. Let's say that I have two integers and I just want to sum them up. So what can I do? I can basically define a lot of different things here. The first thing that I can define is a function. And a function is basically a mathematical function. So in Boogie, when we say function, we don't mean something that is executable. We just mean some abstract mathematical function. So a mapping from the domain to its codomain. So I can have, for example, a function called sum, which takes two integers, and I show it like this, and returns another integer. So what this declaration tells Boogie is basically that sum is a function from n times n to n. So it takes, and by the way, when I say integer here, these are unbounded integers. They're not 32-bit integers. So what I'm saying here is that there is a function called sum that maps, and that takes two integers and maps them to a third integer. At this point, Boogie doesn't know anything else about this function. And this function might not even be computable. It's not a function in terms of C functions. It's a mathematical function. Okay. So now based on this function, I can actually do more things. What can I do? I can define some axioms. And as you know before, an axiom is basically a rule that has no precedent. So it's a rule that it's something that just holds. We assume that it holds. So for example, as an axiom, I can say that sum of 2 and 3 is 5. And we can use axioms for actually defining test cases as well, but that's not what we're going to do today. So we can define functions, we can define axioms, we can define constants. So I can define a constant, let's call it x, and give it a type. So the type of x is int. We can also define new types. So I can define a new type and call it, whatever, let's say color. So I can have a type called color. And then I can have constants of type color. So I can say that, for example, there is a constant called red, and red is a color. There is a constant called blue, and this is a color. We can also do black and say that this is also color. And then I can do all sorts of axioms. And in my axioms, I can also have quantifiers. So for example, I can have an axiom like this saying that for all C that is color, C is either red or blue or black. So I'm saying that only these three colors exist in my universe. I'm giving it an axiom. And you can see the notation for that. So basically we can have for all, and then we have to also specify the type of the object that we are quantifying over, and then two columns should be put between the quantification and the actual proposition, and then you write the logical proposition. And the logical proposition is written in a very similar way to C++. Okay, so now we saw how we can define objects. Now let's see how we can define programs and what we can do with programs. So the way to define a program or a function is to use procedure, and the definition is very similar to function, except that we have this kind of separation in our mind that a function is a mathematical function, but a procedure is something that runs, it's a program. So we can have a procedure, let's call it maybe do sum, and we can use the same notation. It takes two integers and returns another integer. Now, okay, so when we define procedures, note that we haven't still defined how this procedure works. We are just saying that such a procedure exists. Okay. And now I can define preconditions and postconditions for this procedure. So I can, for example, have a precondition, and the preconditions are set by the keyword requires. So I can say requires A greater than 0 and B also greater than or equal to 0. So what this tells Boogie is that we are assuming that every input to this function do sum satisfies these requirements. So the requirements are basically the same as preconditions in our Hoare triples. Then another thing that we have is ensures, and ensures is basically the same as postcondition in our Hoare triples. So in this case, I can say ensures C is sum of A and B. And this makes sense because sum was not some procedure, it was actually a function, a mathematical function. Or I can, well, in case of integers, plus is already well defined, so I can just forget about sum altogether and say that ensures C is A plus B. Okay. And then I can also write an implementation for this procedure, and the way to do that is to use the keyword implementation, or you can just write the implementation directly behind after the procedure, but I do the first thing first and then comment. So I can have an implementation with the same header, and I just implement it here, and I can basically say C, assign A plus B to C. And there are some things that I should tell about our procedures and implementations. The first thing is that you don't need to explicitly return something. So when you put a value into this C, that's the value that is going to be returned. And the second point is that you can, of course, return several things. So you can have, for example, another integer as well. Okay. So now that we have all of this, and let me remove the axioms and everything. Let's just have this. So I can just click here on verify, and it verifies that my program is correct. It hopefully verifies that my program is correct. Okay, yes. So the program verifier finished. One implementation was verified, and there were no errors. So what do we mean when we say that this was verified? Well, we mean that it basically verified the Hoare triple, and the Hoare triple is that this is the precondition, this is the program, and this is the post condition. So it verified that this Hoare triple holds. Okay, now let's do some examples, and let's do more interesting examples. And as we do these things, we will also see some other aspects of the Boogie programming language. So let's go back to the previous thing that I said. Let's say that we have a type called color. And let's say that we have some constant colors, red, blue, and let's also say green. And let's say that I have an axiom that these are the only possible colors. So for all color C, C is either red, or it is blue, or it is green. And so one thing that I can do is that I can say, let's say we have a variable, a global variable called, let's say, selected color, which is the color that is selected right now. And it's of type color. Okay. So the first thing I want to do is that I want to write a procedure called not blue. And the procedure doesn't really require anything. I just wanted to ensure that selected color is not blue. Okay. So let's write an implementation for this, and it didn't take any input, and it didn't really return anything. So by the way, one thing about this language is that if you have a procedure that modifies a global variable, you have to say this explicitly. So in this case, I have to explicitly say that this thing modifies selected color. Okay. So can you give me an implementation for this very obvious procedure? So all I want to do is that I want this implementation to make sure that the selected color is not blue. What can I write in there? So give me suggestions in the chat. Any suggestions? Sure, yes. So let's say I say selected color and just assign some other color to it. So let's assign red or green. Okay. What happens if I run this verification procedure now? Let's see. Okay, the server is down. Let's do it again. Okay, the online tool is sometimes really awful, so let me just do it offline. I can call this draft.ppl. And I can just run boogie and draft.ppl. So there was an error. It says boogie finished with 0 verified and 1 error. And it exactly tells you what the error is. And the error is that a post condition might not hold. And it also gives you the line number, which is, well, in this case, we have only one post condition, which is line 12. So yeah, of course, the post condition that might not hold is this one. Okay. So why is it that this post condition might not hold? Yes. So red can be equal to blue. We haven't really told Boogie that red and blue are different objects. What we have told Boogie is that there is a type called color, and then these are three objects of type color. We haven't said anything else. If their type were different, then of course it would deduce that these are different objects, but their types match, and we have no axiom that says that these are not the same. So what I have to do is that I have to add some axioms. And for example, I can add an axiom that red is not blue, and blue is not green, and green is not red. And now it would work. So if we run it now, the program verified. Okay. So this was a very simple example. Now let's do an example that is a little bit more involved. So Boogie by default has all sorts of operations on integers, but it doesn't actually have integer division and integer remainder. And the reason for that is that these operations work differently in different programming languages. So Boogie doesn't want to really take a side there. So let's just try to verify a simple program that divides one number by another number by just subtracting it over and over again, and see how we can do that. And I'm doing this simple program because I want to actually show you an example that has while loop in it. Okay. So first of all, we have to start by defining the mathematical functions. So let's define a mathematical function called integer division instead. And this function would take two integers and return another integer c. Okay. And we can also have another function for remainder that also gets two integers and returns another integer. Okay, now we can write axioms that give us the mathematical meaning for this function. So the mathematical properties of this mathematical function should be codified as axioms. So how would you write an axiom that defines this function mathematically? And let's say that we only care about positive integers at the moment. So let's say that for all a and b that are integers, what do we have? So this is the fundamental theorem of algebra, I think, which is basically uh, a is equal to the division times b plus the integer remainder. Okay. And let's say that we are only interested in positive integers, so we say a is greater than 0 and b is greater than 0. So I can do something like this. So as you see in my axiom, I can have quantifiers. So I'm quantifying over all a and b that are integers. And I can have all sorts of logical operators, and this is implication. So we put two equal signs so that it's not really confused with comparison. So this is that. Okay. But is this enough for defining the two functions? So if I want to give a mathematical definition of integer division and integer remainder, and let's say that I'm doing it only on positive integers, is this axiom enough, or do I need more axioms? Okay, what do we need? Well, b is non-zero because I'm assuming that a and b are both greater than 0. I'm only talking about positive a and b. Right. Yes. So we need int div, the result of int div of a and b, to be non-negative, and also we need the remainder to be between 0 and b minus 1. So let's write those axioms. For all a and b, there are integers. If a is greater than 0 and b is greater than 0, then a divided by b is greater than or equal to 0. I think constraining the remainder would be enough. Yes, that's enough actually for making it unique, but we need something more, and I will tell you in a moment. So we also need to have this remainder greater than or equal to 0, and also less than b. So from a mathematical point of view, we don't need this axiom. Even if I remove this axiom, these other axioms just give us uh, the value of these functions uniquely. But the problem here is that even though these axioms give us unique values for our functions, at least for when a and b are positive, this is not something that Boogie understands at this point. So the way Boogie understands these axioms is very much in a mechanical way. So what Boogie understands from this axiom is that whenever it had an a and a b which were integers and greater than 0, it can deduce this, right? So we actually need an axiom that gives Boogie the idea about uniqueness and says that these things are defined uniquely. So what we can say is this. We can say for all a, b, c, d, which are all integers, if a is greater than 0 and b is greater than 0 and c is greater than or equal to 0 and d is greater than 0 and less than b, And if A is B times C plus D, triple signs there. If all of these things hold, then we can deduce that C is the result of division of A and B, and D is the result of applying inflam on A and B. Right, D can be 0. And hopefully I have the right parentheses. So basically, when we're defining a mathematical function, we really need to define it on both sides like this. Okay, now we have the axioms that define our division and our remainder. Now let's define a procedure that actually computes this. So I call it procedure. Let's call it do division. It takes an integer a and an integer b and returns an integer c and an integer d. Let's say that it returns both of them. Okay. So what are the preconditions? What should I write as requires? So I said that we are assuming that a and b are greater than 0, so I can add those. And what else? So I wouldn't have any other preconditions, but what post condition should I have? So can you give me the post condition in the chat? Yes. So we have to say, first of all, ensures, and then we want C to be result of dividing A by B, and we also want D to be the remainder. I can use an and here and write them all as one post condition, or I can just break it down into several post conditions. It's usually better if you break it down, because then when you get an error, Boogie would tell you which one doesn't hold. So that's nice. And now I can just write my implementation here, or I can explicitly say that it's an implementation for that procedure. Okay. So what is my implementation? The simplest thing ever. I just let C be 0. Oh, and okay, let's do the implementation first, and then I'll tell you some other quirks of this language. So let's say C is 0, and while A is greater than or equal to B, we just set A to A minus B and increase C by 1. Oh, okay, so when we are defining the function intdiv, which is integer division, we are defining a mathematical function. This is basically kind of like specifying what we want our actual implementation to do. So this is the mathematical meaning of integer division. And then I'm giving a procedure and an implementation. And I want to make sure that it computes the right mathematical object, right? So in order for that to make sense, I have to have a very formal definition of what it is that I want to compute, which is basically intdiv and intrem, which are mathematical functions, and also a very formal definition of how I'm doing the computation, which is this implementation. And then what Boogie checks is that these two match, right? And that's what program verification is at its core. So with these axioms, mathematically, these functions are well defined. Now we just need to make sure that we are computing them correctly. Okay. So I let C be 0, and then I just do subtraction, the simplest way of doing division. And then at the very end, well, C already has the right value, right? And I just need to put the value of A in B. Okay, now let's run Boogie and see if it can verify this. I have to really run this locally. Okay, so just run this. Okay. Yes, we need to say that it modifies. So that's what I wanted to say now. But before that, we have a small error here. Forgot the column. So, and we will get another error right now. And here. So as you see, the error that we have is in line 17. And basically what it's complaining about is that we are changing the value of A. So A is considered to be immutable in this context. We can basically add a modifies here saying that it modifies A, but it's better if we just don't do that, because basically the problem here is that we are using the value of A and also the value of B, which were the parameters of our function in the post condition in the ensures, right? So when I say ensures D is int rem of A and B, which A and B am I talking about? Am I talking about the initial A and B or the final A and B or something in the middle? And this is what makes the confusion. So in order to avoid this kind of confusion, it's just better if you don't change A and B. So instead of that, let's just work with D. I just let D be equal to A, and I say while D is greater than B, make this, and then I will not make this one, right? So I'm starting with a very large remainder. My remainder is all of A, and at every step, I'm just increasing the quotient by 1 and removing B units from the remainder. So it's also a correct way of doing division, of course. And now we run it, and let's see what happens. So I have to run this locally again. So as you see, it actually complains. It says this post condition might not hold, and it shows us which post condition it is. So yeah, it says the post condition at 9. This one, it says might not hold. And it gives us a bunch of more details. So the keyword here in the output of Boogie is might. So it says this post condition might not hold. What it means is that I could not prove the Hort triple. I could not prove that this post condition holds, but it might actually hold. There might be a proof for it. So we have to start and try to help Boogie figure out the proof. So how can we help Boogie figure out the proof? Now think about how we were doing proofs with Hort triples and Hor's rules. Basically, the hardest part in our proofs were always figuring out the invariants. And the problem for Boogie is very similar. So just given this program, it's actually very hard to figure out what kind of invariant it should use in the while rule to prove that this program is correct. So if we can give it some invariants, then it might actually work fine. So let's do just that, and we can do that with the keyword invariant. And what invariant should I give it? So remember that an invariant is something that always holds at the beginning of a while loop. So what invariant holds at the beginning of every iteration of my while loop? Yes. So our invariant is basically that b times c plus d is always equal to a. Now, figuring out this invariant is easy for humans because we just read the program, figure out what it does, and then guess the right invariant. But it's actually quite hard for automated approaches to come up with this because, well, you can do all sorts of expressions with the variables that you have, and why should this specific expression be used as the invariant? It's not like the program verifier can do any magic and figure this out. Okay, so let's see what happens when we run it with this invariant. Okay, there's still something wrong. It still can't quite figure out what to do. So what is wrong? Again, it's complaining about a post condition, right? And it's complaining about the post condition at line 9, this one. But before going to its complaint and trying to fix it, let me just tell you what Boogie is trying to do right now. So you have the precondition and postcondition here, and we have also given it an invariant. Now, Boogie does not assume the invariant. What it does is that it actually tries to prove the invariant. So in this case, it seems it could prove the invariant, but if it fails in proving the invariant, it will also give you an error. So basically, when Boogie verifies a program, you can be 100% sure that everything in there is correct. And that includes the invariants. Okay. So what should we do? Well, let's go through this and see where it can possibly get stuck. So it sets C to 0, sets D to A, and we have this invariant going over and over again. And we also have the assumption that A is greater than 0 and B is greater than 0. So what can it prove at this point? At this point of the program, what assertion can we prove? Well, the loop invariant, of course, holds. So we know that this holds. What else do we know? We also know that because we've reached this point, then the while condition does not hold anymore. Otherwise, we would just go through another iteration. So we know that D is less than B. Okay. And are you seeing the error? Should we just flip the invariant? What do you mean by flipping the invariant? A equals, no, that's fine. So you don't really need to do that kind of things. Boogie is smart enough to figure that out. Okay. But based on these uh, assumptions, which axiom can we actually apply here? Do we need to add D less than B? Yes, we can actually add that here as well, but it's already part of the definition that D is the integer remainder. Okay, maybe we are missing d greater than or equal to 0. Yes, that might be the case. Yes, so let's see what it misses when it wants to apply this axiom, basically. So let's forget about these other axioms and let's just comment them out because we don't want Boogie to get confused and try to use them. For now, let's say that we only have this single axiom. Right? So we have to satisfy its preconditions. We have to satisfy that a is greater than 0, right? So initially, we know that a is greater than 0. But as this while loop just goes on and on, there is no guarantee that that holds unless we give it as an invariant, say that a is greater than 0. And then Boogie will also prove that. So unless you give it an explicit invariant, it's not guaranteed that Boogie will keep this in mind, that a will remain greater than 0. And let's also say that b is greater than 0. Okay. We also need to have a positive or a non-negative c. So let's also add that to the invariant. We also need a non-negative d. So initially d is at least d is a, which is positive. At every step, it's being reduced by b, but it's already greater than or equal to b, so it always remains non-negative, and it makes sense to say this. Okay. So now that I've given it these invariants, what Boogie does is that it tries to prove that these invariants hold at every iteration of the program, of the while loop. And then uses this also to prove the post condition. So let's see if this succeeds. Okay, yes, this succeeded and verified everything. So as you see, the hardest part is really the invariant, and it's kind of dumb when it comes to the invariants. It doesn't really know what to do. And you have to give it the right kind of invariant. Okay. Now I can put the other axioms back as well, but these other axioms, even though we needed them for defining these functions, they are not really useful in the verification process. Okay, so let's do a bunch of other examples as well. So I'm going to basically do maybe 2 more examples. I can do 3 examples. And yeah, the idea is that I want to get to a point where we can see the program that we had in our second homework, which was the program for computing greatest common divisor, and try to see how we can handle that in Boogie. Okay, so now let's go to something else. I actually have the code already over there. Okay. So one thing that I do in my research is that I verify smart contracts, and usually we do it by translating the smart contract to Boogie. So what I want you to look at is now something that is kind of a famous bug in the blockchain community, because this is something that happened and allowed someone to steal more than $150,000. So let's say that the program that you're implementing is basically a wallet, and it keeps some balance for different people. So for example, this balance can be in Bitcoin or in another cryptocurrency. And it also allows them to transfer the balance between themselves. So we define this program by first defining a type person, which can be anything basically. So all this line says is that we have a type called person. And then we also define a balance. And what this means is that it's a mapping from person to integer. So balance is a map that basically maps every person to their balance, which is an integer. And now I have a procedure which does transfer. And let's say that it transfers X units of cryptocurrency from person A to person B. So these are the requirements. So of course, we want for the transfer to record that A is not equal to B, but let's remove that for the moment. And let's just focus on what a transfer is. So what does a transfer do? First of all, of course, it modifies this global variable balance. So we have to say that modifies balance. And what do we want to ensure? We want to ensure that we have conservation of money. So basically, we want to make sure that the sum of balances remain the same. And this is another keyword. So old is a keyword. And the way this works is because we are modifying balance, when we are writing a post condition, we have to have a way of talking about the current value of balance, which is the value after the execution of the procedure, and also the old value of balance. So the way it works in Boogie is that if you just write balance of A, this means balance of A at the end of the execution. And if you write old and then put it as a parameter in there, then this means the value of balance of A at the beginning of the execution. Okay, and then we have an implementation for this transfer, and you can see the implementation. So this implementation is actually incorrect, and it's a very famous bug in the cryptocurrency community. Can you tell what's incorrect about it? And let's say that we don't have any overflows or underflows or anything, so our integers are not bounded. What kind of error do you see here? Yes, so one thing that we really need to make sure is that x is greater than 0. So our assumption here is that this transfer can only be initiated by person A, right? And you want to do some sort of access control. So you want to be sure that A cannot steal money from B. So x has to be non-negative. So let's put this here, and let's say that this is a requirement. So it requires x greater than 0. Yes, so there are two other problems identified in the chat. The first problem that is actually also important and we have to check is that the balance of A is enough. So you have to require that balance of A is at least X, right? But one point here is that note that I don't write old balance of A, because when I'm talking about requirements, I'm talking about preconditions, and preconditions happen before the program is executed. So there is no ambiguity here. When you say balance of A in a precondition, it of course means the old value. But when you use it in a post condition, it can have two different meanings. And this is why we use the keyword old. Okay, but the more important bug actually is what happens if A and B are the same person. So if A and B are the same person, the error that we have here is that basically A is getting free money. And this is what happened in a real world case and let someone steal $150,000. So, but let's see if if Boogie can figure this out. So let's say that this is the input that I'm giving to Boogie. This uh, this program is buggy, of course, and I want to see if Boogie can understand it. So let's transfer that quickly. Okay. So as you see, Boogie fails to verify, and it says that one of the post conditions might not hold, and it shows you exactly which post condition it is. So the one at line 8. But in this case, we have only one post condition. So this is the post condition that might not hold. Okay. And the reason is, of course, because A and B can be the same person. Now, if we add this requirement and say that A is not equal to B, so a transfer can only be initiated between two different people. No one can transfer to himself. Now let's see what Boogie says. Yeah, Boogie verifies it. So this is actually a very simple example showing why we need formal verification. Because if you are a programmer and you have written this code, it is very likely that you forget to write this requirement, but it's almost impossible that you forget to write this post condition if you want to do formal verification. And this post condition itself is enough to remind you that the requirements are not enough. Okay. So let's do another simple example. Let's see. So let's say that I want to do some sort of an auction. And the way an auction works is that, let's say it's an online auction. So people bid and you want to find the highest bidder and the highest bidder wins. So again, I define some type called person. I define a global variable called bid, which basically maps people to integers. So gives me the bid of each person. And I will also have a global variable called, let's say, highest bid, which is also an integer. Now I want to have a function that people can call, or a procedure that people can call and use it to do bidding. So I call that, I don't know, do bid maybe. And let's say that it basically takes a person to do the bid, and it also takes a value x, right? And it doesn't really return anything. So tell me my requirements, and also please tell me my post conditions. So what does this function require and what does it ensure? So let's start with what it ensures. Let's start with the post conditions. Of course, if person A is bidding a value X, I would say that it should ensure that at the end of it, bid of A becomes X, right? But what else should it ensure or require? So think of this as an online system and think that people are just calling this procedure to make their bids. And we're doing an auction, we want to find the highest bidder. Yes, well, at the end of it, we would require that the highest bid is at least X. That's right, but we can actually require something even more stronger than this. So what we want to have as a post condition is that the highest bit is actually the maximum of all the bits, right? So no, it's not just that it's greater than x or greater than the bit of a. We want it to be bigger than all of the bits. And the way I can write this is that for all people b, for any b that is a person, I want to have bit of b less than or equal to highest bit, right? Okay. What else? So we should have this initially as well, right? So I can't just have this post condition out of the blue. Yes, and there should also be someone. This is also a good one. So there should be some person who has actually bid the highest bid. This is good. Yes. But these are in the post conditions. And we should have the same thing in our preconditions, right? So basically, in our precondition, we should also have for all people B, their bit is at most the highest bit, right? And also for all people B, sorry, there exists a person B uh, that has made this highest bit. And let's say that we are only caring about cases where we have at least one bit. So forget about the corner case where it's the first ever bit. Okay, is this all? So what I'm trying to show you is that writing the requirements and writing the specification itself is not such an easy thing to do. And we still need to write some more stuff here. So one thing that we definitely need to make sure is that no one can decrease their beat, right? So I would also require that x is greater than or equal to the bit of a if he had any previous bits, right? But even this is not enough. So what is this saying? This is basically saying that, well, before you run this program, which we haven't written yet, before running the program, all bits should be less than or equal to the highest bit, and there should be someone who has bid this highest bit amount. And then after we run it, oh, and we also require that A cannot actually decrease his or her bit. But then after we run it, all we are requiring as the post condition is that the bid of A is X, and all the bids are less than or equal to the highest bid, and also there exists someone who did the highest bid. Now, here's the problem. I can actually write a function, write an implementation of this procedure that resets all the other bits to 0 and just puts bid of A to be equal to X. Oh yeah, and we also need X greater than 0, right? And if I do that, I can basically change other people's bits and still satisfy all the specifications here. So I will still satisfy all the post conditions. So I need an even stronger post condition. I need this post condition for all people other than A. So if B is not equal to A, the bit should not have changed. I should have bid of B equal to its old value. So as you see, verification is a hard problem, but even figuring out the specification that you want to use for your verification is not such an obvious thing to do. Okay, so now let's do the actual implementation. Okay, and we also need some modifies clauses here as well, because it modifies bid and it also modifies highest bid, and these were global variables, so we had to explicitly say that they will be modified. So we have this procedure. I can just have an implementation for it. And the implementation is very simple. Just set bid of A to X. And if bid of A is greater than highest bid, set highest bid, bid of A. And let's see if this works. I have to do it locally again. Okay, there is an error. So the error is line 14. It says this post condition might not hold. So it could prove the other post conditions, right? So if I remove this, if I comment it out, let's see if it works. Yes, it works without that post condition. So why is it that it cannot prove this post condition? What if bid is empty? Right, but we have a precondition saying that it's not empty, right? Because we have this precondition here that says that there is at least one person whose bid is the highest bid. So basically, the problem here is that the engine that is being used for proving uh, these theorems, these pre and post conditions, is Z3, and Z3 could not really deduce this, ensuring that such a person exists. Now, what can we do? We can maybe try to give it some hints, but this is not guaranteed to make it work, right? So maybe we can rewrite this a little bit. Let's rewrite it and do a case analysis. Let's say if bid of A is the highest bid already, then bid of A becomes X and highest bid also becomes X. Else, bid of A becomes X, and if bid of A is greater than highest bid, then highest bid becomes. Let's see if this works, because at least in one case, we are explicitly showing where this highest bit is. No, it still doesn't work. Okay. So let's see if we can actually give it some more hints. I'm not quite sure if this will work, but because it really depends on the underlying solver. But let's just try to give it some hints. So I don't think it needs a hint here. In this case, I can give a hint, and I do this by assert. So an assertion is basically like an invariant. It's something that always holds when the program reaches this point. And so what can I assert here? I can assert that there exists some B, and this B is of type person, such that B is not A, and also bit of B is equal to highest bit, right? This is something that I know at this point. Let's see if it verifies now. Okay, still not. What are we missing here? This is weird. It should, I think we're missing something because it's a simple thing that it should be able to verify. Let's see. I just comment this assertion out and this ensures out and see if I can get any errors with my assertions. So here I just write the same thing. Exists a person B such that bit of B is the highest bit. Let's see if we can figure that out. Okay, so it doesn't have a problem with this. It can prove it here. So the problem is here. We know that there exists a person B that is not equal to A and has this. So let's just add a else part maybe. Oh, no. Let's see what happens if I put the same assertion here. Okay, so it has an error with this assertion now. So it could verify all of our assertions except for this one. So at this point, we could convince it that there is a person who is not A and whose bit is the highest bit. Okay. The assertion can only hold in the else? No, well, I mean, in this case, oh, right. Not really, right? Because, well, we are breaking it in two cases. The first case was when A was already the highest bidder. And in the second case, we have some other person who is the highest bidder. And either it gets updated or it doesn't get updated. Okay, let's add an explicit assertion here. Oh, right. Oh, I should have removed this. Right. Okay. That's correct. Okay. Now let's see if it can verify. No, it's still giving us an error. So line 33. Still can't figure this one out. Okay, let's do an assertion here, and let's say that access B who's a person, and B is the same as A, and B that B is the highest bit. Let's see if this works. Okay, so it's fine with this assertion, but still not fine with the final assertion there. Okay, why can't it prove the assertion on line 24? Okay, let's actually write an else part. And let's do nothing here. Okay, let's say highest bit is highest bit. And let's have this assertion. I don't know why it's failing. It's quite weird. Yeah, so it basically can't prove this even though it holds. It's weird because, well, if I go this way, yeah, I don't know. I think the theorem prover is just not strong enough. Maybe we have to play with the parameters of the theorem prover to prove this. But anyway, yes, without this ensures it can, so without this existential ensure, it could verify the program, but it can't verify this one. Yeah, this is a bummer, but honestly, these things happen very often. And the reason is that, well, again, we have Rice's theorem, so verification is, in the general case, undecidable. So there are many cases where you see that these automated verification tools just don't work. So they fail to verify. And usually the way this works is that you have to just continue working with it and giving it more and more assertions until you reach a point where it can verify everything. And this is pretty much how we do verification in the real world. So you start by writing all of your specifications and writing your implementation. And then the verification part is really interactive. So you give the specification and the program to the verifier. It fails to verify, gives you some errors. You try to add invariants, then hope that it can verify. Sometimes it does, sometimes it gives you errors. And then you just continue. You add more and more assertions on until you can actually get the verification. And this is what we do for safety critical systems. So the idea is that if you are writing, for example, a smart contract that is a wallet, and if it's going to hold millions of dollars worth of money, you can't really allow any bugs in there. You need to have a proof that is checked by an automated machine, for example, by Boogie in this case, that your implementation is correct. So this is tough luck. Whenever you get into these problems and you see that something cannot be verified, you have to just continue until it can. And well, we're running out of time, but that's probably what I should do as well. I have to just figure out what kind of assertions I have to write here to ensure this one. Okay. So there is a question, what is the pros and cons of Boogie comparing with other tools like Coq? So Coq is basically a theorem prover, and Boogie is not really a theorem prover. Boogie is an intermediate language for writing programs and writing verification objectives. So what Boogie is doing right now is that it's translating this whole instance, this whole verification instance, uh, to an SMT instance, and then giving it to another theorem prover, which in this case is Z3. And that theorem prover is right now failing to prove this theorem. But you can take the same instance and give it to other theorem provers. I think Coq can also handle these kind of instances. So Boogie would be able to probably translate this to an input for Coq as well. But the use cases are completely different. So Coq only focuses on proving theorems, but Boogie is focused on doing the verification and doing the reduction from verification to theorem proving. So any other questions? Okay. Uh, so in that case, have a very good day. And it was a big disappointment that Boogie couldn't prove this one, but let's just work on it and figure out how we can make it work. Okay, see you, bye. Yeah, and I have to remove this from the recording, but nothing that Microsoft makes actually works. See you.